Good morning to everybody. So for me, as I say, it's a pleasure to have here Carl Brozek today. So just a few words about Carl. So Carl graduated at the University of Chicago in 2010. And after that, he moved to MIT to do his PhD with Professor Mirshadinka, okay, working with metal-organic frameworks and conductive metal-organic frameworks. And after that, he moved to University of Washington, where he did a postdoc with Professor Daniel Gamelin, working, I think, in organic nanoparticle, quantum dots, perovskites, and all these type of materials. As I say, he currently is an assistant professor at the University of Oregon, and his research group, or main objective of his research group, is studying the redox processes of nanoscale at the nanoscale gap between small molecules and microscopic materials, mostly focusing on colloidal clusters, porous materials, polymers, and ionolikers. So today he's going to talk about size-dependent behavior of porous nanocrystals. So please, Carl, the floor is yours.
Yeah. So it's really a pleasure to be here. As an assistant professor coming to Spain, this is my first time giving an international set of seminars, and it's really an honor for this to be one of the first places I've ever done that. And it's been very wonderful being hosted by Daniel also, so thank you for having me here. I'm excited to tell you about some of the work that my group has been up to for the last couple of years. Before I do that, I wanted to first acknowledge the people who made all this work possible, a really great group of graduate students and undergrads and collaborators around the world, also the Department of Energy and the National Science Foundation in the US. And before I tell you about, so the University of Oregon is in Oregon, and a lot of people don't know where that is. I also didn't know, even when I was living in Washington, I didn't really know where the University of Oregon was. So it took me a little while to realize where it was. But to help your frame of reference, much like we right now are close to a city called Toledo, University of Oregon is also close to a place called Toledo, just south of it. And a lot like how Barcelona is west of Cairo, Egypt, we're also west of a place called Cairo. So we have all the cities hiding in Oregon. The University of Oregon is in a really beautiful area called the Willamette Valley. The valley stretches from Eugene, Oregon, which is where the university is, all the way up to Portland, Oregon, and everything in between is wine country. We have really excellent wines. The other thing that this area is famous for is we're really famous for track and field. And so Nike spent about $1 billion building this new field just in the last couple of years so that we could host the World Track Championships. The championships just concluded. Spain, I read about, had the largest team qualify in its history of track and field. About 60 people from Spain competed and won numerous medals at the event. So congratulations to Spain. Okay, so research in my group focuses on high surface area materials, porous materials, framework materials. These include metal organic frameworks. We do a little bit of work with perovskites. We study porous metal chalcogenides. And in all of these different research areas, we focus on three main ideas. One of them is how to make these as nanoparticles. We study what I call ion-coupled charge transport. So it's how do charges move through something that has so much empty space and has such high surface area. And then we also study their dynamic bonding properties as well, because we found that these materials are actually much more flexible than a lot of people have thought. So I'm calling these three separate areas, but really all of these focuses are relevant in every project that we study. And I think you'll see that today. Okay, so in the metal organic framework field, a lot of fundamental questions have been studied and a lot of real world applications have been targeted with these materials. It's because you can make them from so many different components. There's something like 100,000 known versions of unique MOF structures out there. And as much as I would like to, when I started my PhD, my advisor said, everyone is studying these for gas sorption and separation. We have to do something different. And so I spent a lot of time trying to do different things. But at the end of the day, probably currently their most industrially pursued direction is probably in gas storage and separation, environmental remediation, separation of chemicals. This is largely because there's one estimate that about 50% of all energy used by industry in the entire world every year goes into separating chemicals. So it's an incredibly energy intensive process. And it's because industry is using these massive distillation facilities, which are very energy intensive. And so one estimate is that if we could switch away from distillation and work more towards membrane-based chemical separation technologies, that we would save 90% of that energy. So people want to make membranes. And the way that people make membranes now is mostly using cellulose acetate. And that's nice because cellulose acetate is readily abundant. It's relatively inexpensive. But the issue with cellulose acetate is it's difficult to chemically functionalize. And so when people use cellulose acetate for separations of CO2 versus methane, for instance, they notice that the performance of these membranes hits an upper limit. And so if you plot the selectivity of a separation versus the permeability, that's basically how quickly the gas molecules are moving through, there's an intrinsic trade-off. The more selective a membrane is, the slower things are going to move through the membrane. And so this upper bound, which was discovered 10, 20 years ago, is called the Robeson upper bound. And people want to improve the performance of these membranes. And one way to do that is by working with materials that have greater chemical tunability. And so in the last 15 years or so, people have become really interested in making these composite membranes where you have the polymer that you would normally use in a conventional membrane, but you embed MOF particles in there. When people were first studying this, these were particles of all different sizes. In many cases, they were actually just bulk crystals. Sometimes the MOF and the polymer are just mechanically mixed with each other. And sometimes people form actual covalent linkages between the MOF and the polymer. And when we did this, people noticed that we actually can extend the performance beyond that initial Robeson upper bound. And so now there's a goal of just constantly pushing that upper bound to greater and greater performance. However, when you work with these sorts of membranes and you're making MOFs from bulk synthetic methods, the membranes that you get can't really be used industrially. And it's because industrially you want to be able to apply about 8 atmospheres of pressure against the membrane. And these sorts of membranes are not going to withstand that. And the reason is because when you work with a bulk MOF powder, not nanoparticles, the particles will actually phase segregate from the polymer. And so you don't really end up with a composite. You just end up with some polymer and some MOF, and then the thing falls apart pretty easily. And so a lot of really nice work has been pioneered by Daniel's group and others, Seth Cohen's group, Jeff Long's group, showing that if we can move towards MOF nanoparticles, you can get them to self-assemble, you can make membranes that are much more mechanically robust, and they should withstand those 8 atmospheres of pressure. But how to make MOF nanoparticles reproducibly of all these different MOFs that we know are out there is really still just beginning. And so my group came in trying to understand, how do we control, for any MOF, how do we control the particle sizes and the morphologies? And so this is where my group first started working in this area. My first student, Checkers, so Checkers likes to dye her hair, and she just, in this photo, she just passed a big oral defense examination, and so I got her flowers to match her hair color. But she's been really fantastic in pioneering this area. And she started off asking which MOFs can even be made as nanocrystals. So we know there's about 100,000 distinct MOFs out there. Which of them can even be made as nanoparticles? What sizes are reasonable? And what chemical factors control the sizes that we get? And so we started off doing kind of a metadata analysis of the literature out there. And this is what we came up with. Of the 100,000 or so known MOFs, it's only about these 20 or 30, and many of them are actually structurally related to each other. Only about these have been reported as nanoparticles. Anything that's a circle is an average or median size, and anything that's a triangle is the smallest size. And what you look at this is that these sizes aren't actually that small. Most of them are sitting in the hundreds of nanometers. rather than 10 or 20 nanometers. And so we wanted to figure out how can we make the particles smaller? How can we make them more reproducibly? And so we wanted to figure out what is the mechanism of how MOFs grow in general, either as particles or as bulk MOFs. And so when people talk about the mechanism of how nanoparticles grow, they typically talk about the Lemire model. And the Lemire model, which is often used for understanding how metal nanoparticles grow, the idea is that you can track the precursor concentration as a function of time. And at some point, you have so many precursors in your solution that they will spontaneously nucleate to make a particle. The concentration drops, and the particles continue to grow through diffusion-based aggregation. Well, the Lemire model assumes that you're working at really high concentrations, and it assumes that there's a separate nucleation and growth stage. And when we were doing this metadata analysis of the literature, we noticed that often nanoparticles of MOFs are made at concentrations that are much lower than the bulk synthesis. So that was unexpected. The second thing is there's some nice in situ studies watching MOF particles grow, which suggested that there aren't distinct growth and nucleation steps. It's just sort of like a continued, almost like a polymer growth. And so we decided that we would need a new model to understand how MOFs grow. And so we developed this model that I won't go into very much today, although I'd be happy to talk about it after. We call it the seesaw model. And this model is really about arrested polymer growth. It treats MOF growth very much like how people treat polymers. And the idea is that if you're trying to get a MOF of a specific size, you stop it from growing any farther by consuming all of the metal ions. And you do that by having lots of linker and lots of modulator. And if you're not familiar with modulators in this field, a modulator is something that looks like a typical MOF linker, but only has one carboxylate normally, so like benzoic acid. And this kinetic trapping process, we argued, is the result of a competition between these different equilibria. Your linker needs to get deprotonated, your modulator needs to get deprotonated, you need to form metal linker bonds, and you need to form metal modulator bonds. And the way that you get small particles is when you form lots of bonds with metal ions very, very quickly. And so with this model, we've been able to reproducibly control the size of lots of different MOFs. So for example, we're focusing on this iconic MOF, copper HKUST1, also known as copper BTC, and we could study how different common synthetic parameters impact the size. And so these three panels, for instance, are almost the same experiment, except each panel is using different equivalents of modulator. And then we plot the size as a function of how much linker, the concentration of linker. And we see that the concentration of linker, as you increase the concentration of linker, you consume more of those metal ions. It does make the sizes smaller, but what seems to matter even more is how much modulator you use, for example. Alternatively, we can say, let's just vary the amount of modulator and track what happens to the size. The reason we call this the seesaw model is because we notice that when you add more modulator, the sizes get small and then they get big again. And so this is the sort of seesaw relationship. So this is what we predicted actually in the model. And so we did something a little different. Rather than just add benzoic acid, we added it as a buffer. And so we varied how much of it was benzoic acid versus benzoate. And so this 33% benzoic acid here, that was a solution that was 33% benzoic acid, the rest was benzoate. And we see that for a fixed amount of modulators, you can control the size of the particles by using buffer synthetic conditions that are more acidic. And so if you increase the acidity of your solution, your particles are going to get bigger. And so we can control the size, but also the morphology. So this is all at the same equivalence of modulator, but we can control the size and morphology. Okay, so this is just sort of a taste of what we can do reproducibly. But now that we can do this, I come from a quantum dot kind of background. So I said, there's a lot of stuff that people can do with quantum dots because they're so small that I want to be able to do with MOF particles. For example, I want to study their size-dependent behavior. Because if they're small enough, we should be able to take advantage of solution state characterization so that we could study the size-dependent behavior. And we want to be able to make thin films really easily. So as sort of a first taste of what we could do, I wanted to study this other famous MOF called MIL-125. MIL-125 is sort of a porous molecular version of titanium dioxide. MIL-125 contains these octameric titanium oxo clusters. And unlike MIL-125, or unlike TiO2, which has a band gap that's fixed at 3 eV, one of the reasons that people really like MIL-125 is because you slightly change the environment around the titanium metal ions, and you change that band gap a lot. So in conventional MIL-125, it's a band gap around 4 eV. If you put an amino group next to the titanium, then you decrease it by about 1.5 EV. And the other reason that we like this MOF is because it's what really kicked off a lot of the photoredox and photocatalysis chemistry that people are doing with MOF. So, so the Fourier group almost 20 years ago showed that you can take this MOF, irradiate it with UV light in the presence of an alcohol, and you trap highly reactive titanium 3+, and the MOF becomes this kind of blackish purple color. So it has interesting optical properties. And we thought, if we can make this as a nanoparticle, maybe we can study its size-dependent optical properties, kind of like a quantum dot. That was the idea. So to do this, we need to be able to make this as nanoparticles, which we were able to do. We can control their size. By controlling the amount of modulator equivalents, we can get that U-shaped seesaw relationship. The titanium precursor that we use also controls the size. We think the stronger the titanium ligand bonds, the lower the concentration of titanium is in the solution. So all this is nice. Okay, so we can make these as particles of different sizes. And we said, all right, so let's study their optical absorption as a function of size. But we wanted to do this without any guest molecules. So no solvent, nothing in the pores. We wanted to look at the intrinsic optical properties of the MOF. And so we took this UV vis spectrum of about 80 nanometer particles. And at the same time, we evacuated and heated the nanocrystals because we wanted to activate them. But when we did this, we saw something really unexpected, that the optical absorption was strongly temperature dependent. Well, that was weird. So we said, we asked, is this true for all sizes? So when we repeat this on larger particles, we still see a temperature dependence, but it's not nearly as severe. And what this reminded me of was how semiconductors in general, so diamond, silicon, germanium, when you heat them, their optical gap gets smaller. But it typically only gets smaller by, I don't know, 100 milli-eV or so, not as severe as this. And so this was unexpected. But how do we think about this? Why does this happen in a normal semiconductor? Well, you can think about it in terms of typical molecular orbital theory. At low temperatures, your atoms are close together. And so that means that the bonding orbitals are really, really low in energy. They're really stabilized. And it means that your anti-bonding orbitals are really high in energy. So that means it's a big gap. But when you heat something, whether it's a molecule or a material, the atoms are going to move farther apart. That means that the orbital overlap gets worse. And that means that your optical gap gets smaller because the bonding orbitals aren't as low in energy. Your anti-bonding orbitals aren't as high in energy. Okay, so that's kind of the molecular picture. Well, we can do this for a variety of sizes with MIL-125. And I'm plotting the optical gap versus temperature. And we see that at a given temperature, the optical gaps are size dependent. So that was unexpected. But then also how temperature dependent they are is strongly dependent on the size. In fact, the smallest particles are the most temperature dependent. And we see that if you heat them about 300 or 400 degrees, the gap shrinks by half an EV, which is really, really big. That's much bigger than in a typical semiconductor. The other thing that we got from this by fitting the data was we get this thing called the Wang-Rees parameter. That's this S value. So the Wang-Rees parameter tells you how different the geometry is of your excited state compared to your ground state. This is true. People use this for organic molecules, inorganic molecules, materials, perovskites. People use this all the time. And so a small S value means that the geometry is similar between your excited state and your ground state. So a typical S value for a molecule is like 0.1, 0.3. And we're getting these Wang-Rees parameters of 10, 20, 30. And so that's telling us that there's something about the MOF structure that is able to change a lot. And that's interesting to us because we like thinking about MOFs as flexible dynamic structures. And that's really different. You know, if you're like Daniel and I, if you started in the MOF field decades ago, when you looked at a MOF paper, this is how they always started. You get this beautiful picture of a MOF structure, and it looks like this must be how it looks. Totally ideal. There's no defects. It's not flexible. But in the last 10 or 15 years or so, we're now knowing that this isn't really the case, and they're much more interesting than just these static structures. And so if you focus on, this is MOF5, if you focus on the MOF5 cluster, and you look at those metal carboxylate bonds, we know that molecular versions of these metal carboxylate bonds are really dynamic, at least for molecules. They're always in an equilibrium between being bound and unbound. So that had us thinking, what if this is true for MOFs as well? And that would be very different from this idea that a MOF structure is just this fixed, rigid thing that you see in the picture. Well, it's also important because it would help explain a lot of really important chemistry that we see in the MOF literature. So for example, if metal ligand bonds and MOFs are dynamic, this would help us understand how metal exchange happens. So there's this bizarre phenomenon that you may have tried in your own lab, where you take MOF crystals, you soak them in a different metal solution, and the metals switch places without destroying them off in a single crystal to single crystal transformation. So how does that even happen? And probably it requires these bonds to be dynamic. There's also a lot of really nice catalysis work where the catalysis involves and must involve the substrate binding to the metal site, but this is often reported at MOFs like MIL47, where there aren't any open metal sites on the metal. And so sometimes it's probably defects, but in this particular case with MIL47, this is a really nice set of papers that showed pretty convincingly that rather than defects, it's actually dynamic linker metal bonds that allow the substrate to come in and get oxidized. Another popular area right now is melting MOFs and liquid MOFs. And when people talk about the mechanism of how a MOF melts, they already talk about these dynamic metal ligand bonds. So this is an important concept, but there's not a lot of evidence to actually show that it happens. And so that was the goal of my lab. Can we actually see the dynamic bonding? So this would be weird for the MOF community, but it's actually totally accepted in the polymer community, metal organic polymers. So for example, in metal carbene polymers and metal pyridyl polymers, this is so well established that people have actually measured the equilibrium constant. We know what fraction of the time the ligands are actually bound to the metals. And like I said, this is for metal carboxylates, it's very well reported for molecular metal carboxylates. And those equilibrium constants are really small. So a log K of 0.5 would mean that about 30% of the time, there's not even a bond there. So imagine what that must mean for a MOF. So this is what we wanted to study. And when you're studying bonds, you often think about vibrational spectroscopy, IR, Raman. And the problem is that metal carboxylate bonds are really, really low frequency bonds. And my thinking was, I figured if you heat these up, you should see more of that unbound state. So we needed to be able to do variable temperature spectroscopy, and we needed to be able to see bonds that were really low frequency. Well, in my lab, we can't do variable temperature Raman or variable temperature terahertz. The best thing we can do is variable temperature IR. And by variable temperature IR, it's much easier to see the CO bond. Now, I figured that even though we're not looking at the metal oxygen bond, we should be able to see changes in the CO bond. We think that really big changes here are going to translate to small but observable bonds in the CO bond. A physicist would call this coupled anharmonic oscillators. In chemistry speak, I think the reason that this works is because the lone pair of electrons sitting on the oxygen that binds to the metal. So this is the MO diagram for a CO bond in a carboxylate. The lone pairs are actually these electrons that are sitting in anti-bonding orbitals or non-bonding orbitals. So what that means is the more you can get that lone pair to stick onto the metal, the more you're getting these electrons out of these anti-bonding orbitals. And that means that the CO bond gets stronger. So a stronger metal oxygen bond means a stronger CO bond. Alternatively, a weaker MO bond means a weaker CO bond. So the hypothesis was you heat up a MOF, and the CO bond should redshift. That's the simple way of saying what I just said. So that was the hypothesis. And so that's what we did. So we picked about 20 of the most common MOFs. I'm going to focus mostly on copper BTC, but we picked the 20 most common MOFs, and we measured their IR spectra as a function of temperature. That's what this looks like. And they redshift. Turns out a lot of these vibrational bands redshift. We were thinking this is probably the asymmetric, this is the symmetric. They redshifted, but so did a bunch of other bands. And so I wanted to know what were all these bands that were redshifting. And so we worked with my collaborator, Chris Hendon, who's a computational chemist. And he helped us assign these bands. And it turns out that every band that was redshifting had some carboxylate character. If a band had no carboxylate character, it didn't redshift. So that's telling us something interesting about MOFs, is that the carboxylate is really localizing all of the structural changes that happen when you heat up a MOF. Everything else seems to be mostly fixed. So that was interesting for us. So we can focus on the asymmetric stretch. When we normalize the data, we see that it obviously is redshifting. It's reversible. So we were worried that we were just destroying the MOF, but it's reversible. You can cool it and it blue shifts. You heat it again and it redshifts. The other thing that was unexpected is that the width of the peak, it gets biggest at an intermediate temperature. I sort of naively thought that you keep heating it, it's just going to keep getting broader, more disordered. But it's actually, it's widest at an intermediate temperature. So that wasn't clear to me why, but it turns out that's really important. So the way we started to understand this is we view this as an equilibrium between the bound states and the unbound states. And so you can think about this as this cartoon potential energy surface here. At low temperatures, you favor more of the tight states, and at high temperature, you favor more of these loose states. And so if that's true, you should be able to see two species in your data. And so if you take the asymmetric stretch, they fit very, very nicely to two species. We actually didn't, when we fit this, we didn't tell the program to fix where those two species are. It did that by itself. It decided that that at low temperature, you mostly have a high frequency species. At high temperature, you mostly have a low frequency species. At intermediate temperatures, you have both. That's why the peak is broadest at intermediate temperatures. Well, the other nice thing about this fit is that the area under those two curves, if you take the ratio of them, it gives you the equilibrium constant. So we can get all this just from fitting normal IR data. And so here, this is the equilibrium constant of that metal ligand bond as a function of temperature. And one thing that was nice to see is that the room temperature value, right about here, is spot on. It's totally consistent with the molecular log K values that I told you before. So it's saying that these metal carboxylate bonds are really acting like these dynamic metal carboxylate molecules that people have seen. So like I said, we've done this for all these different common MOFs. They all do the same thing. And with that, at room temperature, I can tell you what that equilibrium constant is. So this is useful. So when people trying to design some new chemistry for, I don't know, let's say mil 125 or mu of 10, if you're in Valencia and you're studying mu of 10, you can think about how dynamic those bonds are. The other thing is, this is consistent with the idea that UIO66 is the most stable MOF because it has the largest equilibrium constant. But it's still not a very big number, which means that even in UIO66, those bonds are probably pretty dynamic. Okay, well, with the data, we figured we should also be able to understand the energetics of this process. You should be able to fit the data to a Van Hoff relationship. When you do that, you get the curve that I'm showing in blue. It's not a very good fit. And that was surprising. And so we were looking around for other ways to fit the data. And it turns out that you can change the Van Hoff equation a little bit and allow the specific heat of your material to change. When we do that, you get the curve in pink and it fits much better. But why would you let the specific heat change? Well, it turns out people use this model when you're studying something that's undergoing a phase change. So for any kind of material undergoing a phase change, the specific heat goes to infinity at the phase change temperature. So you have to let the phase change. Okay, so what does this all have to do We've got a model that says that we're maybe looking at a phase change. We have vibrations that are redshifting. How does this all come together? Well, I did a little bit of digging, and I learned about something that people call a soft mode. So a soft mode is a vibration that pushes your material so hard that it destroys the material and it causes a phase change. So if you've ever seen these cartoons where you have an opera singer and it causes a wine glass to explode, that's basically a soft mode. That opera singer has hit a resonant frequency of the glass that's causing the glass to move so much that it changes into something else. So people have seen this before for other important materials. So for example, in the perovskite strontium titanate, you can follow the some of the vibrations, and you heat up the material, and those vibrations will redshift until they go to 0 at the phase change temperature, and then they you keep heating, and then they move into a new vibration. So it turns out a lot of phase changes are triggered by a vibration. In fact, when something melts like ice, there's typically a vibration in ice that is causing the water molecules to change so much that it causes the ice to melt. So it turns out it's actually a very general phenomenon. And so if there's a vibration that does it, it's called a soft mode. That's what I'm showing in this cartoon here. So, so these soft modes, they cause lots of phase changes: magnetic, ferroelectric, optical, etc. And so we've become really interested in the idea of maybe MOF metal ligand bonds are actually causing a lot of important phase changes. And maybe we can use that understanding to design new phase change materials. And so just as a first example of this, we started studying a MOF called iron triazolate. And so iron triazolate is a spin crossover MOF. And I'm showing here its magnetic moment as a function of temperature. And so you heat it, it will abruptly go into the high spin state. It'll stay in the high spin state. And then all of a sudden, it'll drop to the low spin state. This is called the hysteresis window. This is one of the largest hysteresis windows of any spin crossover system, molecular or material. Some argue it's the largest. These are also some of the most abrupt transitions. It's not clear why. We thought maybe dynamic metal ligand bonds have something to do with this really bizarre spin crossover behavior. By the way, this is really different from molecular spin crossover systems, where if you heat them, the magnetic moment just gradually increases. Most materials, you get much smaller hysteresis windows. And in the 70s, theoretical physicists predicted that you would get this perfect box-like relationship if you had lots of cooperativity, whatever cooperativity means. That was another thing that was a mystery to me. What does cooperativity even mean? But they said if the energy of your cooperativity was 5 times your thermal energy, then you should see this. So that was this prediction, okay? So we wanted to study this. So we played the same trick. We measured the variable temperature IR of iron triazolate. Here's the triazolate stretch. It's really temperature dependent. So that was nice. But we saw something else, that not only does it redshift, but right at the spin crossover temperature, it inverts and starts to blue shift again, kind of like I was showing you for strontium titanate. In fact, this is exactly the hallmark signature of a soft mode, is you should see it redshift up until the phase change temperature, and then it regains its energy. And so this is telling us that the triazolates are really acting as the soft mode that cause the spin crossover. And so a way of thinking about this is that when you go from a low spin system, the bonds are much tighter, they're much stronger. When you move to a high spin magnetic system, the bonds are much weaker. The reason these dynamic metal triazolate bonds act as a soft mode is because it's a vibration that's taking those strong low spin bonds and it's pushing them, it's stretching them out. And so eventually that vibration stretches them out so much that all of a sudden the MOF switches into the high spin state. So that's how we think it's acting as a soft mode. I was wondering, what the heck is cooperativity? Well, it turns out you can measure it from the data. So cooperativity people often call gamma. The entropy and the enthalpy of your spin crossover, you can get that from calorimetry. So if you have differential scanning calorimeters, you can measure that. So the only thing you actually need is at a given temperature, how many of the metal sites are in the high spin state. That's all you need. And so we can take someone else's data that they collected for this MOF, and we can figure out what gamma is. We plot that as a function of temperature. It goes to infinity at the spin crossover temperature, but you can look at what the cooperativity is away from the spin crossover temperature. It's around 20 kilojoules per mole. Turns out that's exactly 5 times kT. So just as people predicted in the 70s, you get this really sharp box-like spin crossover behavior when you have a huge amount of cooperativity. That was completely consistent with what they predicted. Okay, but we're probably mostly chemists in the room. So what does cooperativity mean? So the way that I think about it is that the bonding in a MOF is sitting in this kind of perfect in-between zone, this Goldilocks zone. In a molecule, in a molecular crystal, the metals, the magnetic centers aren't really talking to each other. They're very loosely connected to each other. And so if one magnetic center goes high spin, then the other ones don't care. You're not gonna, it's like chemical pressure. There's very little chemical pressure on the surrounding magnetic centers. In a typical semiconductor with much denser structures, much stronger bonding, if a magnetic center goes high spin, the chemical pressure from everything else around is really, really high, and it pushes that magnetic center to be low spin again. This is why there are basically no conventional semiconductors that do spin crossover. Whereas for MOFs, we're right in between. The magnetic centers, they're bound to each other, unlike in a molecular crystal, but that bonding is really weak. And so I think that's why. So this is how I think about cooperativity. It's this chemical pressure idea. It's sort of like the peer pressure of how all the neighboring sites are communicating with each other. And so in the case of a MOF, we're just in between. And so it's an example of something that's really unique to MOF chemistry that you can't achieve with other types of molecules or materials. People also predicted that this should be really size dependent, because in models of spin crossover, the magnetic centers that are on the outside, they're the most flexible. And so those are the ones that should go high spin first. And so we wanted to show that this was true. And so we thought, well, let's take iron triazolate and let's try to make it as nanoparticles. And when you make iron triazolate the normal bulk route, the one that was reported, a lot of the chemistry I've been talking about is all done at Spanish institutes, which is, I don't know if that's coincidence or I'm just really inspired by the work that's being done here, but Felipe Gondara in Madrid was actually the grad student who first made this material. When you make this material, it's a bulk MOF, so you're not going to get nanocrystals. But we said, well, let's take the synthetic methods that we developed and let's try to make these as nanoparticles. And so by using methylimidazole as a modulator, we can use very few modulator equivalents, very, very little, and control the sizes from hundreds of nanometers down to just 5 or 6 nanometers, which is among the smallest, if not the smallest, reported MOF nanocrystal. These are also indefinitely colloidally stable, which is totally bizarre. And I was talking earlier about this, about how we don't add any surfactant ligands, and these are just indefinitely stable in DMF. We started this project about 1.5 years ago, and we have particles still sitting in DMF and nothing has precipitated out. So we can take these particles and we can measure their spin crossover temperature using differential scanning calorimetry. Everywhere you see a dip in the data, that's where the spin crossover happens. And we see that for the smaller particles, the spin crossover happens at lower temperatures. And so we can really control that over 50 or 100 degrees just by changing the size of the particles. We also see that in the IR data. So we see that they redshift, for the different sizes, but the redshift it's steeper, it's more temperature dependent for the smaller particles. So this is all nice. So this was a nice sort of proof of concept, but we realized we have these really small particles, and now there's a lot that we should be able to do with them. And so much like has been done at this institute, we showed that we can make transparent thin films. So the yellow bit here is our transparent thin film from these particles on a glass slide. And because we can make these as thin films really easily, we can do 4-contact conductivity measurements. And so here I'm comparing thin films of different sizes in nitrogen and air the particles need to be oxidized in air to be conductive. So in air, everything is about 100 to 1,000 times more conductive. But what was really surprising is that the smallest particles, the thin films of the smallest particles, are much more conductive than the bulk powder. We were wondering why. And so we took the films, cut them open, and looked at them by cross-sectional SEM. And it looks like the bulk, in contrast to the bulk particles, the smaller particles are just sticking together much, much better. There's much less open space. And so basically, particle to particle conductivity is much better. And so yes, we're not looking at the conductivity of a single nanocrystal. This is thin films, but this is useful because if we're going to be using MOFs for thin film type applications, this is a really useful insight to know that we probably need to be working with smaller particles to make more effective, stronger membranes, much like has been demonstrated in this institute. Okay, so we can make these really small. What else can we do? So it turns out we can run solution phase electrochemistry. So to the best of our knowledge, this hasn't really been done before, where you take a colloid of a MOF and just run a normal CV. And so we saw these CV traces that almost look like molecules, molecular electrochemistry, multiple fairly reversible redox waves. But what's weird is that this MOF, for all intents and purposes, really just has one type of iron site. And yet we're seeing redox waves that differ from each other by hundreds of millivolts. That's really weird. Because think about it, the difference between ferrocenium and decamethylferrocenium is about half a volt. And that's one of the best examples of how you can tune a redox couple of something. Here, this should all be the same iron chemistry. The environment should be the same, and they're differing by almost a volt. So something weird is happening here. So we thought, is this an impurity? We tried, these were the 25 nanometer particles. We tried this on all the different sizes, and we see something really similar, multiple fairly reversible waves. So what's going on here? So we wanted to get a little bit deeper insight into what's causing this. And so we cast them as thin films, because now we can do that. Cast them as thin films on a glassy carbon electrode. We used acetonitrile since they don't suspend in acetonitrile. We see CV traces that are pretty similar. So multiple pretty reversible waves. This is all done in TBA PF6. And we realized that iron triazolate actually has pretty small pores for a MOF. You know, you think about a MOF, the pore could be 1 nanometer, 2 nanometers, but in iron triazolate, it's only about 5 or 6 angstroms. And so we started to worry that maybe PF6 is actually too large to go into the pore. And so we started to think that maybe the less positive redox feature, the easier to oxidize iron, maybe this is iron that's on the surface. And maybe the reason you have these other redox waves at really positive potentials is because that's the additional energy that it takes to try to oxidize the iron sites that are on the inside. So we repeated this measurement, but with BF4. So we moved to a smaller anion and everything changes. There's more redox waves, they're sharper. Depending on how you assign them, they've moved to less positive potential. So everything gets easier. So this was consistent with this idea that the redox chemistry of a MOF is really governed by how easily you can compensate those charges. Well, we wanted to dig a little bit deeper. And so we used something called a quartz crystal microbalance as our electrode. It's a piece of quartz that resonates at a frequency that depends on how heavy it is. So you can track the mass of your electrode by using a QCM electrode. And so we repeat these experiments. First, I'll just show the current. So we plot the current in PF6 versus BF4. It looks like what I showed you before. We can count up the charge. When we use the bigger PF6, you oxidize about 1/3 of the iron sites. When you use the smaller BF4, you oxidize about all of the iron sites, so it gets easier. But at the same time, you can watch the change in the mass. And so in both cases, the mass increases as you oxidize the material. That's consistent with the anions going inside. So they increase in both cases, so that's good. But the biggest mass increase happens at that potential, at that feature that was really, really positive and really sharp. And it turns out that when you see really sharp CVs like this is how people think about phase changes, or how people think about solvent reorganization and intercalation chemistry. And so this is really consistent with this idea that out here, you're oxidizing iron sites, you're barely doing any intercalation. But the way that you get this oxidation to happen on the inside of the nanocrystal is you provide all of this overpotential, and then all of a sudden, the BF4 anions, they desolvate, they intercalate, they go into the nanocrystal, and now you can oxidize the iron sites. The last thing I want to talk to you about is the optical properties of these things. So they're so small that that's a photo of the 6 nanometer particles. They just look like molecular solutions. You make them bigger, they scatter more light. So we can measure the solution state UV vis spectra, which is unusual for a MOF. Normally you have to use solid state techniques. The gray data, this is the bulk iron triazolate. All the color traces, these are all different sizes. And so we can focus on the different sizes, and we saw something pretty strange. So these are the 2 different charge transfer bands, these 2 bands here. And we can plot their energy as a function of size. And they redshift. So this is exactly what you see in the quantum dot literature. You make cadmium selenide bigger, and the band gap gets smaller. It redshifts. And so this is still an open area for us, but this is really unexpected. And this is the first time that something as complicated and interesting as a MOF structure has actually demonstrated this sort of size-dependent band gaps. And so we're working with theorists, and hopefully I'll be able to tell you about exactly why this is happening next time I talk to you guys. They also fluoresce. So here are the UV vis spectra. You see there's a slight redshift as you change the size, but the luminescence is in the dash data. There's a huge shift in energy, change in energy between. So, we would call this a really big Stokes shift. Normally, the energy that something fluoresces should be really similar to the energy where it absorbs. But here, there's a redshift of about 1.5 EV. And we think that this gets back to this idea of the dynamic bonding in MOFs, the really big S value, the really big Wang-Rees parameter. You excite, and then when you relax in the excited state, the geometry is so different from that dynamic bonding that it fluoresces at a really different energy. And the last thing I'll say is that we can do this not with just iron, but we can extend the synthesis to most of the first row transition metals. I'm not showing it. We can also do it with chromium. And they all fluoresce, and they all fluoresce at energies that are different from each other. They're different from the linker. They're different from the individual metal salts. And so I think as MOF chemists, we can agree that the goal is always to show that you can do something with a MOF that's greater than the sum of its parts. It's greater than what you can just do with the individual isolated components. And I think that's what we're starting to do here with this new family of nanocrystals. And so hopefully I showed you that by developing a new molecular model of understanding how MOF particles grow, that we can do some really neat solution state spectroscopy and understand size-dependent behavior that's inspiring a lot of directions in our lab, and we're hoping will inspire directions in labs around the world. With that, I'd be happy to take any questions, and thank you for your attention.
Such a wonderful talk. Thank you.
Thank you.
So it's time for questions.
Thank you. Really inspiring talk. I will start with a question related with the beginning, the role of the modulator, because as a MOF chemist, I've always been puzzled by the modulator, because at the beginning they were using this a lot to get single crystals. Mm-hmm. And now you very convincingly show that if you control the amount, you can use the modulator to make really, really small crystals. So, and that's why this C wave.
Exactly. Yeah.
So which is the turning point? What makes the modulator at the beginning behaving like I guess it's sequestering metal ions and suppressing growth, and at some point is promoting the single crystal growth?
Yeah. So it's a great question. So in the US, we call it ICE tables. When you're studying acid-base chemistry, we say, okay, I'm giving you an acid and a base of these concentrations. What is the equilibrium mixture in the end? Students hate it. It turns out it's even worse when you try to do it for this, because it's not just 2 equilibria that are competing. It's it's the 4 or however many equilibria that I was showing. But we tried it. And so Checkers and I sat down and we said, let's start off with a normal amount of different linker and modulator in metal. And let's actually try to calculate how many of these different metal ligand modulator bonds you get. And what we see, it's described in the 2020 ChemSci, not the 2019. And we show that the inversion that you start to, so basically what happens is when you add lots of modulator, you increase the proton activity so much that you shift this equilibrium and you make so much protonated linker that you can no longer trap the particles. And so we have this graph where we show this and this as a function of how much modulator. And you see that they invert. Initially, when you add a little bit of modulator, you mostly are making this and not a lot of this. And then at some point you make this, and that inversion, it happens to occur at the pKa of the modulator. Okay. So when the activity of your reaction mixture looks like the pH of your modulator, then that's when that inversion happens. Yeah.
Very interesting. No, then I have very clear. Thank you for this. And just a bit general question. With all your techniques, can you assess a bit, have you observed that there is a different degree of flexibility in this metal bonding of the surface of the metal ions and the inner part of the column, now that you can control so well the particle size? Because for me, is the surface chemistry of MOFs is also an area that is not very well.
Yeah, I mean, so that's our hypothesis. You don't have a good technique for seeing that. I mean, we think that the reason the smaller particles undergo spin crossover at a lower temperature is because we think that you have more of the surface, and the surface metal ligand bonds are more flexible, and so it can happen. So we have a lot of indirect evidence. I mean, for example, the fact that the Wang-Rees parameter is smaller in the smaller nanocrystals is another example of maybe you have more surface. I also think that the size-dependent band gap, I think that's also you have more flexible surface, but we don't have direct evidence of that yet. Yeah.
Okay.
We're working on it though. Yeah.
Really nice.
Yeah, thank you.
More questions?
Thank you for your talk, and I'm very interested in your study on the size and the morphology on MOFs, because my project requires the homogeneous uniform MOFs, and I want to ask a question. I saw that your work has studied the concentration, the amount of ligand, and the modulator, their effects on the size and morphology of MOFs. And I have this question, and that do you think that the scale of your synthesis will affect the size and the morphology? Because I'm sorry.
Yeah.
Because I've been using this MOF mu88, and I synthesized in a small scale.
Yeah.
And I scale it 5 times and 10 times.
Yeah.
There's some size and the morphology change.
I'm sure. Yeah.
But the concentration, the metal ligands ratio, they're the same. I just scaled it up. So I want to ask, do you think that this will affect the size and morphology?
Yeah. So I think the simple takeaway from all of this is I think you want the lowest possible metal concentration locally. And so if you could have anything that I think is going to cause the metals to be closer to each other locally in solution is going to cause you to have bigger particles. And so in your scale up, if somehow you're not controlling for that, or it's easier for the metal. So like something that we've tried, we haven't published this, but like syringe injection with stirring and different local concentration, we're starting to see that this all impacts polydispersity a lot. But I think what matters most is making sure that you have very slow release of low concentration of metal. So the last slide I showed was showing that we can make the zinc version of that MOF. It turns out the only way to make small particles of the zinc version is we start off with zinc oxide, which is a really weird precursor, not zinc acetate, not zinc chloride. Those make particles that are way too big. And I think what you need is something like zinc oxide that very slowly releases zinc. And so it very slowly releases zinc, and then the ligand, then you have all the ligand modulator, will kind of trap it, and then you get small particles. And so I think, the other thing is making sure that these are dispersed throughout the solution. And so that, when people think about like burst nucleation, like you get really small metal nanoparticles through burst nucleation, you have lots of nucleation happening all really far away from each other. So in your scale up, you want to make sure that somehow that slow release of metal ions is happening, dispersed throughout your solution. Yeah.
Thank you very much.
Thank you. More questions? No, I can ask one or two while they are thinking more. First question is, I like a lot of this dynamic bonding. Are you expecting any change in this dynamic bonding when you don't have solvent inside the channels, or you change the solvent inside the channels?
Yeah. It's unpublished, but we have work. So this is mostly under vacuum, but we've looked at UIO66 and other MOFs, but specifically UIO66 in the presence of different solvent. And the more strongly coordinating the solvent, the less it will redshift. So in fact, we're thinking like maybe you can use it as like a sensor or something, because like really low, like they're not even wet, they're just exposed to like solvent vapor, and you see that it affects the redshifting. Yeah.
Okay. And another question is regarding the spin crossover. When you decrease the size at 5 nanometers, for example, do you think we can still talking about cooperativity, or you are closing too much to the molecular regime in which the most important is how the molecules interact between them and not how are interacting inside the crystal? Yeah,
that's an interesting question. It's certainly possible. When we said we made 6 nanometer particles, we're like, how much MOF do you actually have in 6 nanometers? And I had a picture here of what 6 nanometers might look like. And it turns out that it's actually, it's a good amount of material, but it is approaching this sort of molecular cluster limit. I think you could be right. And the other thing that's hiding in here is like, why does this get so broad? Whereas this really looks like a sharp cooperative thing, are we looking at sort of a distribution of molecular kind of interactions? So I think that could be right. Yeah.
Okay. Any other question?
Yeah. Well, this might be a bit of a philosophical question.
Please, those are the best.
According to your data, where mildly low temperatures are the ideal scenario where both the bonded and more of an ionic species are present, why are we always pushing for high solvothermal temperatures for achieving high crystalline materials?
Yeah, it's a great question. And I think when I had that slide of why do we care about dynamic bonding, I think it's because this is how MOFs grow, is that you need, the reason we can get these big, beautiful crystals is because the bonding is so dynamic. And so I think you need the high solvothermal conditions, one, so you decompose your DMF and you make a little bit of the base, but then also because you're encouraging that reversibility. Yeah.
Wouldn't that be favored at 60 degrees where both species are?
Oh, yeah. I don't know. For this particular, maybe this means that for copper BTC, we could be making the crystals at smaller temperature. That's certainly possible if you have the base in there. Yeah, I don't know. Yeah.
Thank you.
Yeah.
Okay, I think it's time
Okay.
to close. So let's thank again
Thank you.
Carl
Yeah.
for going to talk.